Hello, this is Serene from Exam Help Lab. Today I'll be solving Physics Paper 2 AS Level Structured Questions 9702 Paper 2 Variant 3 October-November 2018. Question number 1, Part A, mass, length, and time are all SI basic quantities. State 2 other SI based quantities. So one is current, which is in amperes, and the second is temperature, which is kelvins. Part B, a wire hangs between two fixed points as shown on figure 1.1. A child's swing is made by connecting a car tire to the wire using a rope and a hook. The system is in equilibrium with the wire hanging at an angle of 17 degrees to the horizontal. The tension in the wire is 150 newtons. Assume that the rope and hook have negligible weight. Part 1, determine the weight of the tire. So since the system is in equilibrium, tire's weight, which acts downwards, must be equal to sum of all the forces that are acting upwards. And the forces that are acting upwards are the vertical components of the two tensions over here, which are equal in magnitude. So for the left part, the vertical component is going to be 150 sine 17. And for the right part, it is going to be again 150 into sine 17. So our weight is going to be equal to sum of these two forces. So 2 into 150 sine 17. Hence, the weight of the tire is 88 newtons. Part 2, the wire has a cross-sectional area of 7.5 millimeters square and is made of metal of Young modulus 2.1 into 10 to the power of 11 pascals. The wire obeys Hooke's law. Calculate for the wire the stress. So stress for the wire is equals to tension in the wire divided by the area of the wire. So tension in the wire is of magnitude 150 newtons divided by area of wire is in 7.5 is in millimeters square. We'll convert that to meters square by dividing it by 1000 square, and you get a stress in wire as 2 into 10 to the power of 7 pascals. The strain for the wire, so we can use the formula Young modulus is equals to stress over strain, where strain is equals to stress, which is 2 into 10 to the power 7 in the wire divided by the Young modulus of wire, which is 2.1 into 10 to the power of 11, and we get a strain of 9.5 into 10 to the power of -5 with no units. Question number 2, part A, what is meant by kinetic energy? So this is the energy due to object's motion. A moving object will always have kinetic energy. An object at rest will never have any kind of kinetic energy. Part B, a cannon fires a shell vertically upwards. The shell leaves the cannon with a speed of 80 meters per second and a kinetic energy of 480 joules. So suppose this is a cannon, it moves upwards, it rises up in the air with initial speed of 80 meters per second and kinetic energy of 480 joules. The shell then rises to a maximum height of 210 meters. So it covers a distance, vertical distance of 210 meters, and a maximum height means it has reached the maximum height it could cover with final velocity as 0. The effect of air resistance is significant, so we're not going to consider air resistance as negative 9.81 because air resistance is significant. So show that the mass of the shell is 0.15 kilograms. That can be calculated with the help of the formula kinetic energy is equals to half mv squared. Kinetic energy at the starting point is 480 joules, half mass of the shell is unknown, and the speed with which it starts to rise is 80 meters per second, so 80 squared, and we get mass of the shell as 0.15 kilograms. Part 2, for the movement of the shell from the cannon to its maximum height, calculate the gain in gravitational potential energy. So gravitational potential energy is equals to mass into g into height, where mass of the shell is 0.15 G is 9.81, and the maximum height it covers is 210 meters, and the gain in gravitational potential energy is 310 joules. The work done against air resistance. So according to a law of energy conservation, loss in kinetic energy of the shell from the starting point should be equal to gaining gravitational potential energy until the finishing point, which is when it has reached its maximum height. But here you have seen that gaining gravitational potential energy is not equal to loss in kinetic energy. This means that some energy is lost as heat in surroundings, and that is the difference between the gain in gravitational potential energy and the loss in kinetic energy. So this was the loss in kinetic energy, and this is the gain in potential energy. The difference between them is the work done against the air resistance. So that is of 170 joules. Part 3, determine the average force due to the air resistance acting on the shell as it moves from the cannon to its maximum height. So average force is going to be equal to average work done against air resistance, 170 joules divided by the maximum height it covers, which is 210 meters, and the average force due to air resistance is of 0.81 newtons. Part 4, the shell leaves the cannon at time t is equal to 0 and reaches maximum height at time t is equals to capital T. So at this point of time where it has reached its maximum height, its final velocity is 0, so I'll mark this, and it starts with maximum speed of 80 meters per second. So at time t is equals to 0, I'll mark that it had a maximum velocity. On figure 2.1, sketch the variation with time t of the velocity of the shell from t is equals to 0 to t is equals to capital T. Numerical values of v and t are not required. So velocity will decrease with increase in time due to air resistance and the fact that it's moving against gravity. Now the question is if the graph will be having a slope like this or it would be like this. Let me tell you that while the shell is moving up in the air along with decrease in its velocity, its acceleration also decreases. As a result, we'll have a graph which has a decreasing gradient with negative acceleration, which is because it is moving against the gravity. It is rising up in the air, since gradient of velocity versus time graph tells nothing but acceleration. So it's going to be this one, a curve with negative gradient and decreasing too. So a decreasing acceleration and negative acceleration because it is moving against the gravity. It is rising up in the air. Part 5, the force due to the air resistance is a vector quantity. Compare the force due to air resistance acting on the shell as it rises with the force due to the air resistance as it falls. So force due to air resistance increases with velocity. As the ball rises up in the air, its velocity starts to decrease, so that force decreases too and acts downwards. When the shell falls, air resistance starts to increase and the force due to air resistance now acts upwards. So I can say that when the shell rises, force due to air resistance decreases and acts downwards. While when the shell falls, air resistance increases and now is acting upwards because it's always going to act against the object's motion. Question number 3, part A, states Newton's second law of motion. Newton's second law of motion states the equation F is equals to m into A, where A is equals to V minus U divided by T. So I can write that resultant force is equals to mv minus mu divided by t, that is, force is directly proportional to rate of change of momentum. Part B, a toy rocket consists of a container of water and compressed air. As shown in figure 3.1, water is pushed vertically downwards through a nozzle by the compressed air. The rocket moves vertically upwards. The nozzle has a circular cross-section of radius 7.5 millimeters. The density of the water is 1000 kilograms per meter cube. Assume that the water leaves the nozzle has the shape of a cylinder of radius 7.5 millimeters and has a constant speed of 13 meters per second relative to the rocket. Part 1 showed that the mass of the water leaving the nozzle in the first 0.2 seconds after the rocket launch is 0.46 kilograms. So mass is equals to density of water multiplied by the volume of water that leaves the nozzle in first 0.2 seconds after the rocket launches. So here they have written that water that leaves the nozzle has got a cylindrical shape with the radius 7.5 millimeters, which is 7.5 into 10 to the power of negative 3 meters, and covers a length of 13 meters every second, as it is written over here, that it has got a speed of 13 meters per second. So it covers 13 meters of distance every second. So volume of water that leaves the nozzle in just 1 second is pi. Radius of cylinder is this square, and the distance it covers every second is 13. So this is the amount of water, or this is the volume of water that leaves the nozzle in every second. So in 0.2 seconds, 4.6 into 10 to the power of negative 4 meter cube of water will be leaving the nozzle in the first 0.2 seconds after the rocket launch. So now mass is equal to density of that water is 1000 multiplied by the volume for the first 0.2 seconds, and you get 0.46 kilograms of water. That's proven. Part 2, calculate the change in momentum of the mass of water in B part 1 due to leaving the nozzle. So before moving through the nozzle, water is at rest. So we can consider that our initial velocity is equals to 0, and at leaving the nozzle it has got a speed of 13 meters per second, as it is written over here, that it moves with a constant speed of 13 meters per second. So our final velocity is 13. And the mass of the water that moves in B part 1 is of 4.46 kilograms. So change in momentum is equals to mass into V minus U. So 0.46 divided by 13. And we get change in momentum as 6 newtons second. The force exerted on this mass of water by the rocket, so force is equals to change in momentum divided by the time taken for this change of momentum, and that is 0.2 seconds, the first 0.2 seconds. So that gives me a force of 30 newtons being exerted as mass of water by the rocket. Part 3, state and explain how Newton's third law applies to the movement of the rocket by the water. So here you have seen that this amount of force is being exerted on 0.46 kilograms of water by the rocket, means again the same amount of force will be exerted on the rocket by 0.46 kilograms of water, but in the opposite direction, and that's what explains Newton's third law. So I can write that rocket exerts 30 newtons of force on water. So water also exerts 30 newtons of force on the rocket, but in the opposite direction. Part 4, the container has a mass of 0.4 kilograms. The initial mass of water before the rocket is launched is 0.7 kilograms. The mass of the compressed air in the rocket is negligible. Assume that the resistive force on the rocket due to its motion is negligible. For the rocket at a time of 0.2 seconds after launching, show that its total mass is 0.64 kilograms. So the container has its own weight of 0.4 kilograms, and at time t is equals to 0 seconds, it has a weight, the water has a weight of 0.7 kilograms, and 0.2 seconds later, after the launch of rocket, it is left with 0.64 kilograms of water, because this amount of water has already left through the nozzle. So resultant force is equals to mass into acceleration, where resultant force on the rocket is going to be due to the rocket's weight, which will act downwards, and the force being exerted on the rocket from the water that acts upwards. So the force from the water that acts upwards is 30 newtons minus the force due to the rocket's weight, which is 0.64 into 9.81, and mass of the rocket is 0.64 into the acceleration, and hence you get acceleration of 37.07 meters per second square. Question number 4, part A on figure 4.1. Complete the two graphs to illustrate what is meant by the amplitude A, the wavelength lambda, and the period t of a progressive wave. Ensure that you label the axis of each graph, so you have to label the axis too. So I'll start by labeling amplitude and wavelength. Amplitude is always taken on the y-axis, where we have got displacement, let's say, and wavelengths are taken on the x-axis with distance on the x-axis. So amplitude is the highest displacement or the maximum displacement, whereas the wavelength is the distance between the two successive crests. So this is the wavelength of this wave. While we have got over here the period, so period t is taken on the x-axis, where I can label this as time, and period t is the time taken for one complete wave. So one complete wave is again from one crest to the other successive crest. So I'll take this as t. This is the time period for one complete wave. Part B, a horizontal string is stretched between two fixed points x and y. A vibrator is used to oscillate the string and produce a stationary wave. Figure 4.2 shows the string at one instant in time. The speed of a progressive wave along the string is 30 meters per second. So this is the speed. The stationary wave has a period of 40 milliseconds. Part 1, explain how the stationary wave is formed on the string. So I can write that wave reflects at either end, like maybe x or y, and both incident and reflected wave superpose, and that's how a stationary wave is formed. Part 2, a particle on the string oscillates with an amplitude of 13 millimeter. At time t, the particle has 0 displacement. Calculate the displacement of the particle at time t plus 100 milliseconds. So let's suppose I've got this waveform. Where according to the previous part, which says that this stationary wave has a period of 40 milliseconds, means for one complete wave, I will be labeling it 40 over here, and then 120. It says that it has an amplitude of 13 millimeters, so this height will be 13 millimeters. While on the x-axis we have got time period. It says that at time t the particle has 0 displacement, so these are all the points where all the nodes will be lying. Means it's going to be either this, 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 or this. I'll assume that the t we are discussing over here is actually this one, which is going to be 20 milliseconds. So I'll suppose that t is 20 milliseconds. The displacement of the particle at time t plus 100 milliseconds. So I'd suppose that t is 20 milliseconds, so 20 plus 100, which is 120 milliseconds. Again, at this point, the displacement is 0, so we have got 0 millimeters. The total distance moved by the particle from time t is equal to time t plus 100 milliseconds. So from time t is equals to 20 milliseconds to time t is equals to 120 milliseconds. the particle travels from here until the first antinode, which lies here, covering 13 millimeters of displacement on the y-axis, and it continues to move this way until t is equals to 120 milliseconds, covering a total distance of 13 multiplied by 10, which is 130 millimeters, because from here until here it covers a distance or a displacement of 13 millimeters, and from here until here it again covers a displacement of 13 millimeters. Every half of a cycle it covers 26 millimeters of displacement. Part 3, determine the frequency of the wave. The frequency is equals to 1 by time period. The time period of the stationary waveform over here is 40 milliseconds. So 1 divided by 40 into 10 to the power of negative 3. So we get a frequency of 25 Hertz. The horizontal distance from X to Y. So from X until here, we have got one complete wavelength of a wave, and from here until here, we have got half of a wavelength. So first we need to find what the wavelength of this waveform is. So wavelength is equals to speed divided by frequency, where speed we had over here is 30 divided by 25, and we get a wavelength of 1.2 meters. So from X to Y, we have 3 by 2 of wavelength in total. So 3 by 2 multiplied by 1.2 meters, and we get a distance of 1.8 meters between X and Y. Question number 5, part A. A particle of mass m and charge q is in a uniform electric field strength E. The particle has acceleration a due to the field. Show that q by m is equals to acceleration by electric field strength. So electric field strength is force by charge, where force is equals to mass into acceleration divided by charge, and so charge divided by mass is equals to acceleration divided by electric field strength. Part B, the particle has a charge of 4e, where e is the elementary charge. The electric field strength is 3.5 into 10 to the power of 4 volt per meter. The acceleration of the particle is 1.5 into 10 to the power 12. Use the expression in part A to show that the mass of the particle is 9u. Note that this is not in terms of kilograms, but the unit u. Okay, so every u contains 1.66 into 10 to the power of negative 27 kilograms. Now we need to find the mass first in kilograms, and then we'll convert that to unit u. So charge is of 4e. Every e contains 1.6 into 10 to the power of negative 19 coulombs of charge, divided by the mass is equals to acceleration is 1.5 into 10 to the power of 12 divided by the electric field strength. And so we get mass in kilograms, and that is 1.49 into 10 to the power of negative 26, and we will, this is in kgs, and then the cross multiplication of 1.66 into 10 to the power of negative 27, and this mass we can deduce that this is 9u. Part C, the particle is a nucleus. State the number of protons and the number of neutrons in the nucleus. So a nucleus with a charge of 4e and mass 9u. The number of protons is going to be equal to the charge, which is 4, and the number of neutrons is going to be the difference between the mass number and the charge, which is 9 minus 4, and that's 5. Question number D, a second nucleus that is an isotope of the nucleus in part C is in the same uniform electric field. State and explain whether the electric field produces for the two nuclei the same magnitudes of force. So an isotope of a particle with charge of 4e and 9u mass will have a charge of 4e but different mass number, because isotopes are supposed to have the same number of protons but different number of neutrons. So yes, there's going to be the same force, because electric force in this field depends upon the charge on the particle which is the same in both the nuclei. Part 2, acceleration. So acceleration is going to be different because both nuclei have got different masses. But same electric force. Question number 6, part A, define the coulomb. They're asking you to define the unit coulomb, but not charge. So unit coulomb is ampere second. Part B, an electric current is a flow of charge carriers in the following list. Underline the possible charges for a charge carrier. So a charge carrier will either have a charge of 1.6 into 10 to the power of negative 19 coulombs, or its multiple. So none of these except this 8 into 10 to the power of negative 19 and 1.6 into 10 to the power of 19 itself is possible for this charge carrier to have. Part C, the diameter of a wire ST varies linearly with distance along the wire as shown in figure 6.1. There is a current I in the wire at end S of the wire. The diameter is D and the average drift speed of the free electrons is Vs. At end T of the wire, the diameter is 2D. On figure 6.1, sketch a graph to show the variation of the average drift speed with position along the wire between S and T. So at end S, we have got a drift speed of 1. So I'll start from here. So according to formula, current is equals to NAVQ, where cross-sectional area is inversely proportional to average drift speed. At 1/4 movement from S means we have not covered half, but 1/4 of the distance between S and T. Diameter is going to increase from D to 5/4D. So our new drift speed is going to be equal to 1 by the area, which is also equal to radius square. So our new drift speed is going to be equal to 0.64. So at 1/4 of the distance from S, it's going to be 0.64, which may be lying over here. Now at halfway to T means we have reached this point. Our D must have become 3/2 of D. So our new drift speed is going to be equal to 1 by 3/2 square, and that's 0.44 Vs. So halfway through ST is going to be 0.44, which must lie here, somewhere here. Now, when we have reached the point T where the diameter has increased from D to 2D, our new drift speed is going to be equal to 1 by 2 square, and that's 0.25 of Vs. So at point T, we're going to have this. So in short, we are going to have a decreasing curve. Question number 7, part A, state Kirchhoff's first law. So this is about conservation of current. So sum of currents entering into a junction is equal to sum of currents leaving that same junction. Part B, a potentiometer is connected to a battery of electromotive force of 9.6 volts and negligible internal resistance as shown in figure 7.1. The maximum resistance of the potentiometer is 800 ohms. A resistor R of resistance 400 ohms is connected between the slider and an X of the potentiometer. Part 1, state the potential difference across resistor R when the slider is positioned at end X of the potentiometer. So suppose this slider has been moved to this end of the potentiometer. So at end X, we can consider that the length of potentiometer being covered, this is the potentiometer, at this point of the jockey, we are going to consider this length as 0. So resistance is also going to be 0 since they are directly proportional to each other, and the voltage is going to be 0 too, because we start to take lengths from this point of potentiometer. So at end X of the potentiometer, the potential difference across a resistor R is going to be 0 volts. At end Y of the potentiometer, suppose that this jockey has now moved to this point Y. Now we can consider that length is going to be maximum and resistance is going to be maximum too, as they are directly proportional, and the voltage is going to be maximum too. So the maximum voltage that could reach resistor R is 9.6 volts. So at end Y of the potentiometer, PD across R will be 9.6 volts. Part 2, calculate the potential difference across the resistor R when the slider is positioned halfway between X and Y. So the condition is that now the jockey has been moved to halfway through X and Y, just like it is in figure 7.1. We can use ratio of either length or resistance to get PD across a component. When it says that the jockey is put halfway through X and Y, our new circuit would look like this, where I have a 400 ohms of resistor. That 800 ohms of resistor has now been divided into two new resistors, and because it is halfway, it says that the jockey has now been put halfway through X and Y. So 800 gets divided equally into 400 and 400, and this 400 is in parallel connection with the other 400 ohms that was already there in the first part, and the EMF of the battery was 9.6 volts. What we can do is, and the question is asking us to get the potential difference across resistor R, which is this one. What we can do is take ratios of resistance to get PDs. Now, the voltage across this 400 ohms and this 400 ohms is going to be the same since they are in parallel connection with each other. So instead of taking V across just this resistor R, I can take V across this whole parallel connection. So I'll consider that as V divided by the total V applied to the whole circuit, that is 9.6 volts, is going to be equal to the resistance of this whole parallel connection, that is 200 ohms, divided by the resistance of the whole circuit, which is 200, and then plus 400, that is 600 ohms. Again, V and R, they are going to be directly proportional to each other. So this way, I can derive that potential difference across this whole parallel connection, or potential difference across resistor R, is going to be 3.2 volts. So this is the end of the paper. Thank you for watching.